So last time I was talking about the churn classes. So our definition was that if you have a E locally free on X, then I could try to define the churn classes in this formal fashion. I write the so-called churn power series. So I'm looking for a definition of this thing to define all of them together, and we had already the Segre classes. Right? And then the definition was that this is defined to be 1 over ST. Right? That was just an equivalent formula. And then the point was that, for example, SIs, there were in principle infinitely many of them, but CIs, all but finally many are 0. That's one of the properties. So I wrote down various properties. I don't think I should perhaps recall them, everybody remembers what they are. But one of the things involved in the proofs of some of the non-trivial properties, both the fact that CI E equals 0 for I bigger than rank E, this was one important property, unlike the SIs, which there were sort of infinitely many of them. Another important property was the one about exact sequences, that if you have 0 to E prime to E double prime to 0 exact, implies CT of E is the product CT E prime times CT E double prime. So the proofs of these two properties, which are sort of different in some sense from the properties which we already had for SI, they were kind of new properties of some sort. Those things we proved, or I said could be proved using the splitting principle. So splitting principle, I did recall the statement last time and people waved it away saying we understand that fully well from the previous lecture. Very good. So I wanted to say the splitting principle, one consequence was that if I had an E, then there exists a map F y to X, a splitting map for E. So this is flat of a particular relative dimension. So I wrote that as equidimensional, and at the same time it's proper. And we had a third condition, that the flat pullback from the Chow groups of X to the Chow groups of Y are injective. In fact, split inclusions. Okay, so these were properties of such splitting maps, and there are many, there's no uniqueness about them, you can construct them perhaps in several different ways. So, for example, if you want to prove this property, the game was, I apply the splitting to the pair of vector bundles E prime and E double prime. So, okay, what would splitting say? With all, of course, it has these things, such that in the end, of course, it splits. So, in other words, F upper star E is filtered. So, I have a finite filtration F dot of F upper star E, and if I use Kapil's language, grade dot F of E of F upper star E is L1 direct sum LR, where R is the rank. That was the main point. Any LIs are line bundles. LI and pick X, pick or Y actually, pick after pullback, line bundle upstairs. And so this was these were the properties of splitting maps. And then I asserted that claim. Again, this was proved earlier, but I wanted to go through it again just for conceptual reasons. CT of F upper star E is equal to product I equals 1 to R 1 plus C1 Li times T. So of course this implies that on this side it's a polynomial in T, on this side it's the full Chern series. Therefore the Chern classes of F upper star E vanish after some stage, but this F upper star, you haven't lost any information by going to Y. So the Chern classes at the X level itself must have been 0. That's one of the conclusions you get. The second conclusion is if you have such a formula, and if I got the splitting, the filtration and so on by first filtering E prime, also filtering E double prime, right? So if I filter E prime, then I get an induced filtration of E, but where the lowest portion instead of being 0 is E prime, but then E prime itself is filtered. Construct such a filtration which is compatible with the exact sequence, which you can do. Then apply this formula to each of the three things, and then you get the fact that CT multiplies. So all the properties follow immediately once you've got that claim. And of course the claim, for it to make sense, I have to have these line bundles. Originally they are not there, but after going to the splitting place I can construct. Okay, so how does this work? So Amit Hogari must have done it, but I want to also go over it again because I think it's useful to see how to think about it, and I might actually use some of the same tricks for other proofs. So I don't want to just take it as a black box. So let me write a lemma. Suppose E is a vector bundle of rank R on X such that E is filtered by line bundles L1, LR, and also there exists S, a global section of E with 0 scheme Z. What that means is S is a map OX to E, so it's equivalently a map E dual to OX, but then this factors through an ideal inside OX. Right? If I have any map like this, I can dualize it, I'll get a map. But there's no reason that just because this is injective, that need not be surjective. The image is the ideal, that is the scheme of zeros. Right? This is how you do it in scheme theory. So that's my Z. Okay. Then the assertion is, for any class alpha, in Chow Kx, if I look at the following product, so the assertion is this belongs to the image of Chow K minus R Z to Chow K minus R X. That's my assertion. So each time I take the cap product with C1 of a line bundle, it reduces the dimension by 1. So doing it with R line bundle, of course, will go from Chow K to Chow K minus R. But inside Chow K minus R, I have a distinguished subgroup, the image of Chow K minus R of this particular Z. So I assert that the result of that calculation lies in the image. That's the assertion. It's a kind of support condition. So we'll see why this is correct on the one hand, and then how in a sort of formal way, something like this implies this. Both of the arguments are things which actually, in some fashion, generalize, I believe, to many other situations. So it's good to know how to do this reason. It's some sort of formal argument of some kind. So that's what I wanted to say. So okay, so proof. I don't know if this is how Amit introduced something like this at all, but it doesn't matter. There's no harm done doing it again. For example, if you looked at those notes which I had given a link to Sudarshan, which is on discussing things like this in topology. A very similar argument works in topology. So, okay, so here we'll see how that works. So let S, okay, so let L1 be E mod F1E. So let's take the lowermost quotient and call it L1. And if I have a global section of E, so S belongs to gamma XE, maps to say S bar in gamma X L1. After all, L1 is the quotient of E, I take the section, take its image. So now, of course, here it may have some zero scheme. So if you want to think of it like this, I have OX to E and then E mapped to L. So I got OX to L. This is S, this is S bar. And if I look at the dual picture, I'll have OX receiving something from E dual, and that receives something from L dual. Right? So this is also essentially S bar, and this is essentially S. So the image of S is some ideal, and that ideal contains this ideal. Right? Therefore, if Y is the zero scheme of S bar, then our original zero scheme is actually contained in Y and contained in X. Okay. Now let's look at this L1 Y S bar equal to D is a pseudo divisor. On X. So I started with an alpha in chow kx gives rise to C1L L1 cap alpha, which is sort of the class of D dot alpha in chow k minus 1 x. But we know that in fact D dot alpha already makes sense in chow k minus 1 of mod D, which is another Y in our example. So this class here, C1L cap C1 L1 cap alpha, actually belongs to image of chow k minus 1 y to chow k minus 1 x. And the calculation, so to speak, I have also made sense of the pre-image here. I'm saying, in fact, I have this element d dot alpha, which is some, I can call it alpha y or something, some object here. And this is my pre-image, it goes there. If I now want to compute the product of all of the C1s and then apply it to alpha, I can of course apply C1 L1 to alpha and then apply the product of the remaining ones to the result. But that calculation, instead of doing it on X, I can now do it on Y. So this is some new element alpha Y, and I have I have the vector bundle F1E restricted to Y, the vector bundle of rank R minus 1. Well, I have two possibilities. I could have this is the zero vector bundle. So then Y equal to Z, and I have proved the result. So if R is equal to 1, there's nothing to prove. So I might as well assume R is bigger than 1, and I'm attempting to do a kind of induction. So this is now a vector bundle of smaller rank on some scheme Y. I've got S is in fact a global section, S restricted to Y is a global section of F1E restricted to Y. Because Y was the place where S vanished in the quotient. So S in fact lies in the subsheet after restricting to Y. With zero scheme, the same Z, but now theta is sitting inside Y. And by induction, product I equal 2 to R, C1, of course, I can take Li restricted to Y, functoriality of Chern classes, cap alpha sub Y, this new thing, belongs to image chow k minus R of Z mapping to chow k minus R of Y. And now, of course, I pass to X. So the result follows like this. And one of the key points to notice, how well you set up the theory in the beginning, X might have been a very nice thing. You just took some filtration, took some sections. In the middle, whatever you get can be completely general. And you may not get actual Cartesian divisor at all. You may only get pseudo divisors. So sometimes I took the trouble to set up the whole theory of pseudo divisors in order to be able to do this computation. This is one of the key things which you can do with this. Okay, so it's an important technical point. Sometimes I bother to go through the details so that I can make this comment, if you like. Right, now that we've got this, I claim then we can prove all our properties if you want on the Chern classes. The point being that we want to prove something like this claim, this splitting thing. So F upper star E is filtered by line bundles, but right. So in fact, the way the computation is done is something like this. The way we define the Chern class of E, or of F upper star E for that matter, is to define it indirectly in terms of the segregate classes, which in turn are defined in terms of the projective bundle. So though I have a splitting map Y to X, I also have the projective bundle of E mapping to X. So in other words, I have a diagram like this. This is F and this is pi. And then of course I have P of F upper star E. Let me maybe call it pi F or something. Sorry, this is, what have I given this any name? I'm not sure. Anyway. So you have this diagram in any case. Remember that pi upper star E had this tautological line subsheaf, line bundle. Okay? Right, in my notes I should have written somewhere a comment that without loss of generality, I can assume that E itself is filtered by line bundles. Li. And then I want to prove the property on X itself rather than pulling it back under some map. I mean, X and Y are, equivalent spaces as far as we're concerned from this point of view. And you haven't lost any information in the process. You proved something after going to the splitting thing. Of course, the original Chow groups are faithfully reflected, and so you have the same identity. So then I don't need to bring in a Y at all. I can just work with this itself. So what I've done directly in my notes without any explanation, and I also found it confusing for a second. So, right. The point is, this is now filtered by line bundles of pi upper star Li. Correct? E was filtered, pi upper star E of course is filtered. And I have this line subbundle. So what I do is I twist and notice that OPE sits inside pi upper star E tensor OPE of 1. Now this is also filtered by line bundles. What are the filtering line bundles? They're of the form pi upper star Li tensor OPE of 1. But in addition, there's a section of this vector bundle. This corresponds to a global section with empty set of 0. It's nowhere vanishing. So if I look at this lemma, the Z could have been the empty set. So of course the image of the Chow group of the empty set is 0. So that's just saying that the product is actually 0. Therefore I get the conclusion that product I equals 1 to R C1 of pi upper star Li tensor well, so let me write like this, plus C1 of O E E of 1 is 0 as an operator. This you just expand out and rearrange, do a little algebra, you get the conclusion which we want. Okay? So let me not belabor that too much. A little bit has to be done, it's something we still have to do. We get an identity. That identity involves powers of this C1 O1. Then I can apply pi lower star to that identity. That's what would give me back the SIs. The SIs are what? You take powers of O1. I want to look at SI as an operator on something. I take a power of O1, apply, take the cap product with the pullback, and then push the result down. So the point is, this is a formula in the ring of operators of some kind on the Chow group upstairs. If you have such a formula, so this formula is so this element is the thing which I had called zeta, right? So this is a polynomial, a monic polynomial of degree r in zeta. Okay, maybe I'm just not saying this well. This, if I expand out this polynomial, it's just saying zeta raised to r plus sigma 1 zeta raised to r minus 1 plus dot dot plus sigma r equals 0, where sigma I is ith elementary symmetric function in C1 F upper star C1 L1 so on F upper star C1 LR. Okay, I just get such a formula. This is a formula involving powers of zetas and then some sigmas, and notice that these sigmas are themselves F upper star or something. So when I apply F lower star, those sigmas will become the same sigmas below. That part of it is fine. Of course, when I want to apply F lower star, I don't mean F. Do I mean F? I mean pi, I guess, right? Pi upper star. Sorry. F was something else. Okay? So this part, if I take pi lower star or some sigma I applied to something, that sigma I below applied to the pi lower star of the thing. Okay? Now, what are the things I'm applying it to? It's some power of zeta times some class. Well, I can multiply this equation by any power of zeta that I like. So I can make the powers of zeta as big as I want. So I'll exactly get stuff which look like SIs of some class on the other side. So I'll get a bunch of equations. And then those equations can be transformed into this. The algebra is done in the notes. Let me not spend time. Anyway, you've seen other proofs of this. The main point somehow, all this is just by calculation. This is the thing to notice, that after pullback, because there was a tautological line sub-bundle, I can twist by the inverse bundle, and then there's a tautological nowhere vanishing section. And the property of being filtered by line bundles, even if you tensor with a line bundle, the new vector bundle still has the same property. These are the formal aspects, and then you have to do the calculation. You can't do the rules. It comes out. Notice though that the lemma which I wrote down proves more than I really needed for this. That's why I did the lemma work. I need it when the Z is non-empty possibly. I'll need to use it somewhere else if the Z is non-empty. The same lemma. But for this purpose, nowhere vanishing section was a special case. Okay, right. Okay, so that allows us, of course, to we have got essentially the full formalism we need to study things related to Chern classes. CT of E. So in other words, it says CIE is equal to ith elementary symmetric polynomial in what are called the Chern roots. So what are the Chern roots? So basically if I have this splitting map for E, if F was a splitting map, okay, so let me say it like this. You just take the total Chern polynomial CTE, which is 1 plus C1E times T plus CRE T raised to R, and I factorize this in a formal way, 1 plus alpha I T. And there's no such given factorization. But if I choose a splitting map and I think of the CTE pullback, upstairs on such a splitting variety, these alpha i's become the C1s of those line bottoms, right? So there is some overring in which things map injectively, and in that overring I can do a factorization. So I can now behave as though there's just some formal factorization, there's some sort of variables. We call them the Chern roots. Individually, like roots of an equation when we do Galois theory, the individual roots, so to speak, are not well defined, but functions of the roots which are symmetric under permutations are meaningful. So if I write down any, if f of x is a polynomial, let's say in Qx, and I form the expression f of alpha 1 plus f of alpha r, I can rewrite this in some formal way, g of C1 CR, right? Because an expression like this, f of alpha 1 to alpha r, is symmetric in the alphas. So the general theorem on elementary symmetric functions tells me that any such rational polynomial in R variables, which is symmetric in under permuting the variables, is expressible uniquely as another rational polynomial in the elementary symmetric functions. But the elementary symmetric functions are the CIs. Therefore, I get some polynomial expression in the CI. This is a part of the formalism, right? Okay. Sorry? Huh? Even with Z. So Q, and of course similarly with Z or C or any ring of characteristic 0, or probably any ring. Yeah. Commutative associative ring maybe with identity or something. You know. Okay, it's a very general assertion about symmetric functions. So I can do, I mean, there are many ways I can write a symmetric expression even starting with a polynomial in one variable. This is one. Another one is take product I equals 1 to R, fx alpha I. I can look at this expression. This is another symmetric. I can do more complicated stuff, but these are two very obvious things I can do. Already they give very interesting things for bundles. So now I'm starting to get towards the actual Riemann-Roch picture. So I want to talk about the Chern character and the Todd class. So if E is a vector bundle of rank R, I'll define the Chern character Sometimes I have to consider the Chern character on different spaces, so I might put the space x there in the notation as well, if I want. So this is going to be, I take summation I equals 1 to R is the rank of exponential of alpha I, where alpha I are the Chern roots. So in other words, this is sum n equal to 0 to infinity, alpha 1 power n plus alpha r to the n over n factorial. I just write this formally. What this means is that in each degree n, I get a polynomial with rational coefficients in the Chern classes, which is homogeneous of degree n with the appropriate weights. So I would want to think of this as degree 1, and Ci, I think of it as weighted homogeneous of degree I, and CR is of course degree R. That's the same as saying the original alpha i's, which I used in order to build them, are all taken to be of degree 1. It's the usual grading. Okay? So in terms of alpha, if I take this particular polynomial, alpha 1 to the n plus dot dot plus alpha r to the n for any n, that's certainly a homogeneous symmetric polynomial in the R variables. And this is one of the standard polynomials, the so-called Newton polynomial or whatever they call it. So that is expressible in terms of elementary symmetric functions in some fashion. There are some various inductive rules for these things. In any case, that's the thing which you take in degree n. So this is the, in other words, churn of E is by definition, or I can think of churn T E if I want, as sum n equals 0 to infinity, churn n E times t raised to n, where churn n E is the thing obtained from this symmetric expression. Right? That makes sense. I'm working with Q coefficients because the expression here has a factorial in the denominator. So I'm forced to introduce Q coefficients here. Absolutely. So churn makes sense, churn character makes sense only with rational coefficients, or bigger than Q coefficients, right now. Of course, it may happen, so to speak, that no, not only that, the element churn NE, which is some expression, if I evaluate it on some alpha and then take its degree, which is the sort of thing which I said the Hirzebruch-Riemann-Roch will involve such things, you would apparently get only a rational number, but it may be for some reason it's an integer because it's Euler characteristic of some sheaf, for example. Therefore, that whatever integer I got from the numerator is actually divisible by n factorial. Things like that will follow from this. But in any case, right now I can write this. I can make sense of it. So how does it look more explicitly? So it will start with rank E plus the first churn class of E without any coefficients. But the second term will be C1E squared minus C2E over 2 plus so on higher order terms. And this is the so-called churn character. So what are some properties of this churn character? Why is this particular one singled out? I could have done it with any F, or I could have written more general things. This has some special properties. Let's list them. The particularly good choice. Incidentally, maybe I should have said there's no, of course, when I write it with this T here, it's clear to you that it's some kind of formal series. And the coefficient of T to the n is some operator. So it's basically writing down a sequence of operators, which are homogeneous of different degrees. But even if I just try to directly make sense of this infinite expression, whatever it is, as an operator on some alpha, on some space x, x is some variety, so it has some finite dimension. So it has only finitely many Chow groups. Any homogeneous polynomial in these churn classes of degree n bigger than the dimension of x is anyway the zero operator. So in that sense, on a given x, this expression anyway stops. Even though I wrote exponential, so to speak, I took exponential as something which is nilpotent. That's the style in which this works. Okay? On a given x, if you want to discuss what's called Riemann-Roch algebra, talking about abstract rings with operators and things like that, you have to put in hypotheses to ensure such nilpotence. But the things coming in geometry like this are automatically nilpotent because varieties have a finite dimension. So there are only finitely many non-zero Chow groups. Okay, so I have this thing. So what are some of the properties of this churn character? They are as follows. For example, 1, if 0 to E prime to E double prime to 0 is exact, then the churn character of E is the sum of the churn characters of E prime and E double prime. That's one property. But there's another remarkable property. For vector bundles EF, we have that the churn character of E tensor F is the product. Now there are lots of things which might have satisfied this sort of additivity, but at the same time to satisfy this is a non-trivial property. So the Chern character is very basically characterized as the operation which does both of these things at the same time roughly. So let's see why are they true. For the exact sequence it's obvious, because if I have a short exact sequence like this, the usual way that, one way of saying it is that the total Chern of this is the product of those two total Cherns. So therefore the Chern roots of this are union of the Chern roots of this and this. And I'm just taking sum of exponential over the thing, I break the sum into two terms, right? That's, in a formal way, that's how I do it. And then, anyway, that's fine. Tensor product also is a similar kind of thing, because if you think of it like this, suppose you have some, yes, or at least Chern roots. I use the fact that the underlying polynomials, to say this is some universal property about polynomials which are symmetric functions of some underlying variables which I can think, there's a way I can do it without explicitly appealing to splitting principle. That's that whole Riemann-Roch algebra thing. Yeah. But in any case here, let's say the alphas, if you're worried about what is the meaning of the alphas, use splitting principle and alphas are C1s of the line models. So, So why is this identity true? This is just saying product I equals 1 to R. Sum I equals 1 to R alpha x of alpha I. And if I write this side, it will be the product of sum I j equals 1 to S x of some beta j, right? Alpha i's are the Chern roots of E and beta j's are the Chern roots of F. There's no reason the ranks are comparable in any way. Then this is of course sum over ij x of alpha I plus beta j, right? It's bilinear, right? Expanded out. And then if I take a term multiplied by a term, exponential has the property that the exponents add up. Of course, that's a formal property of the usual, that's a property of the usual exponential function, but I can view it as a property of the exponential power series. The exponential power series has this formal property that if you have two variables x and y, x power x multiplied by x power y is x power x plus y in the power series ring in x plus y, in two variables x, y, if you like. Yeah? Of course. That's correct. That's correct. Restatement of what? Yes, right. So, and the claim is this is of course whatever you would get from here. Because if this is filtered by line bundles, that's filtered by line bundle. There's a bi-indexed filtration where the quotients are one line bundle from here and one line bundle from there. C1 of a tensor product of two line bundles is the sum of the two C1s. So that would be exactly taking alpha I plus beta. So this is this thing is defined so that these two properties work. Very good. But what is taught? There's another thing called taught class that I'll just write down right now. So for this, I'll start with Qx is equal to 1 upon 1 minus e to the power minus x, which can be expanded in a series in this fashion. This is something called the kth Bernoulli number. Is that the spelling of Bernoulli? Are there two I's in it? Okay. I'm not sure of this I, but my impression is it might be there, depending on how you. Bernoulli, okay. Right. So there are these numbers, Bernoulli numbers, which come in various contexts in mathematics, and they appear here also in this series. You can, if you like, take this as one of the definitions, then whatever other context you have to. The standard place Bernoulli numbers come is if you write 1 to the k plus 2 to the k plus 3 to the k plus n to the k. You want to write this as some p, some function of n. Bernoulli numbers appear when you attempt to figure out what is this polynomial, right? If k is, well, anyway. Yeah, but the point is the formula might come because of this series. I mean, in other words, that's anyway, different. Which came first? Right. This is probably anyway known already to people before Bernoulli, one presume, right? Euler is after or before Bernoulli? I'm a bit vague here now. Euler is afterwards? Could be. All right. Anyway, this is the kth Bernoulli number. Fine. It appears in various places and we do this. So I have this series. So now what I do is I take Todd of E or Todd X of E if I have to specify the space to be product I equals 1 to R Q of alpha I. So alpha 1 to alpha R, the Chern roots. I can define anything I like. Why this particular choice? What's special about it? Let me start writing out a few terms. It turns out to be, if you do all the calculations, 1 C1e upon 2 plus C1e squared plus C2e divided by 12 plus C1e C2e divided by 24 plus, and then more complicated, minus C1e to the 4 plus 4 C1e squared, there are typos in my notes, C2e plus 3 C2e squared plus C1e, C3e minus C4e, the whole thing divided by 720 plus and so on. Correct. But something else should immediately strike us. This appeared in the Riemann rock for curves and this appeared in the Riemann rock for surfaces. So whatever weird power series this is, it captured two terms which were interesting in Riemann rocks before. So it has something to do with Riemann rock. That at least we should believe after seeing this. It's not what I would call a very categorical perspective in mathematics. You look at a few examples and make a guess that there must be some relation, but I think that works quite well for intuition and guesswork. You do get interesting things. So let's notice though the following property is formally obvious. Todd multiplies. Chern, remember, added, but the way Chern was, I took some function and took the sum of the values of the function at the different alpha I. Instead here I took the product, so naturally, you know, it's with respect to that operation that it's additive, so to speak.
So what is the set of basic properties so that we can work out the formula?
Let me give you something else. I won't answer that directly.
I'm asking what is the set of basic abstract properties of this function?
Well, any power series gives rise to an additive characteristic class as well, and if the power series is a unit, meaning gives rise to a multiplicative characteristic class, and more or less this is sort of an equivalence. That's there in Hitzebrook's book, right? There are things like this. Take a look at it. No, the point of the book is to set up a formalism. He says there's a formalism. things like that. I don't remember the detail, but I know it's there in the book. It's due to him. The observation that basically it's one power series and one variable or sort of what are involved for various things. So let me write a lemma here, which I think in a different sense will tell you something about taught class. And for me, it's some of the explanation of taught class. Lemma is of course due to Grothendieck in principle, but the proof was written down in this paper of Borel and Serre. So if E is a vector bundle of rank R, then sum P equals 0 to R minus 1 to the power P churn character of the pth exterior E dual is equal to the top churn class of E multiplied by the taught class of E dual. So this identity is really, if you like, the proper definition of the taught class. Taught class is whatever you have to put here in order to compare the top churn class of E and this alternating sum. Right now, why would you want to make such a comparison is not maybe immediately clear. I'll come to that later. But you'll see at some stage, we'll have a way of thinking of the churn class of E, the top churn class, R is the rank. But that way will somehow come with some geometry, with some causal complex associated to it, and I can try to use that causal complex to recompute that churn class in some fashion. This is something which might arise from a causal complex. It doesn't exactly match. There is something going on, and there's a correction factor you have to put. If you do the computation, that's what you find out. And that's the factor which you're forced to put. Taught is what else you have to put there in order to make the formula work.
Clear that divides this.
Nothing is clear right now. Maybe it's clear to some people. Grothendieck, probably the whole thing was clear right away. But for us, at least I think we'd have to stare at it too. But I think this identity somehow, to me, explains what, yeah. And it's going to come in the proof, you'll see. Very nice.
Realize that the degree 0, the low degree terms of the left-hand side vanish.
Yes. So in other words, yeah, if you write this, each individual churn character has many terms, right? So this side is already in the rth Chow group. And above, yeah, exactly. So you're saying all the lower ones vanish. And the higher ones can be computed by some record. Yeah, but probably from some perspective, because this is true, that binomial identity is correct. I mean, somehow, is the philosophy, I think. Anyway. Yes, exactly. Exactly. Some property of causal complex. Anyway, all right. So, okay, anyway, let me work out a proof of this. It's not... yeah. The left side is this in terms of churn roots. Correct? If I have churn roots alpha 1 to alpha r, then the churn roots of the pth exterior power are just the sums of the thing taken p at a time, right? Because it was there in the formula. But I put dual here. There's some signs involved. So basically, here you put dual, here you put CRE, there again you put dual. So later, maybe I should make this comment. Later when we understand certain other things about E, if E happened to have, E is a vector bundle of rank R, suppose it happened to have a section, and the zero scheme of the section happened to be a nice codimension R subvariety inside some nice smooth ambient space, then to say E has a section which vanishes, it means I have a map OX to E, and then when I dualize, I would have got E dual to the ideal of the zeros sitting inside the OX, right? So the point is there's a causal complex of the structure sheaf of Z, the zero scheme, as an OX module in terms of exterior powers of this E dual. So that's sort of what's appearing here, roughly. The terms of that causal complex are somehow what are appearing. So I guess what one is saying is that the Chern character of this object is equal to the top Chern class multiplied by this. So this is a kind of Riemann rock, if you like. It's the difference between the top Chern class and the Chern character of this E, of that zero. Yeah, it also turns out the cycle associated to such a Z is CR of E in Chow upper R of X. Huh?
That's the second theoretic remark. Zeros of the vector.
No, and I'm going to prove it in some fashion. It's going to come, or at least it will be incorporated into the discussion somewhere. But later on, that's what we'll find out. That there is a way, in good cases, of understanding what the top Chern class of E is, if it has a section, and if the zeros of the section are a subvariety of the correct codimension, and if the ambient space is non-singular. If all those properties are correct, then the class of that same Z is a representative of the top Chern class. The Chern character is the thing which is additive in exact sequences, not the Chern class. Chern class has total Chern class multiplies, there's some much more complicated sort of formula, okay? Chern character is what works. So when you put the character, somehow you find, on the one side, of course, you'll get the character of the resolution, and then on the other side, I'll get the character of this object, which we have to compute. Z is some subvariety of X. I'm computing the Chern character on X of that subvariety. So that's like Chern character of push forward or something. So that's part of the Riemann rock formula. Anyway, just other explanation. Don't worry if that didn't make sense later on. Whatever I do will patch things up. Anyway, let's start. This is the expression on the left side. So I think of this as product I equals 1 to R of 1 minus X Prof minus alpha I. Right? I mean, it's obvious. And this in turn I rewrite in this fashion: alpha 1 dot alpha R times product I equals 1 to R 1 minus X power minus alpha I divided by alpha I. And I just took this same expression, I divided and multiplied each factor by alpha I. So here I put an alpha in the denominator, and there I collect all those alpha i's out there. But of course, the product of the alpha i's is CR of E. And what was the Todd class? Todd class said, take the Chern roots, take, where is it? Where is the formula? Here. This. So Q alpha I is just 1 upon 1 minus e to the minus alpha I. But what did I do here? Exactly. So E dual is the same expression with plus alpha I. So Todd of E dual should have been product of I equals 1 to R 1 upon 1 minus e to the alpha I, which I should be able to rearrange into this sum. Why is that correct? I don't see it right away. Can I write the wrong formula for Todd? One second. It's possible. I think you're correct. I made a mistake. The formula for Todd involves the x. I have a typo on my notes. If I put x equals 0 in the original formula, it's 1 upon 0. So I'm in trouble. So the point is, if I take 1 minus e to the minus x and expand out a series, it starts with x. Now I cancel off the x, and what's left is the dot series. This is a mistake. I was thinking it looked too simple somehow, but anyway, I could figure out where the problem. So now the claim is it will. Why is it now okay? Of course, exponential I can take it up and down and up, multiply and divide, do something. But I'm a bit puzzled. I got the alpha in the denominator. No, I make a mistake. Yeah. How do I say it? Somewhere I missed something. Okay, the statement is correct. I might have made some mistake in the computer. Let's fiddle around with it and check it and come back to it later. Okay? It follows in some simple way like this.
And this is just a formal policy equality.
Right now there is no geometry.
This is equal to
Exactly. So, but you have to have the right definition. So, the QX appears to have an X here.
So really the point is CR divides the difference.
No, and also I want to know what is the ratio explicitly. I want to compute the ratio is a characteristic class obtained by taking product of things. That's what you have to know. Those are the properties which I want. That whatever it is I get there as the ratio, that is something obtained by taking a power series in one variable and then multiplying it on the churn root. Yes. So in fact, if my calculation, if I had done the computation correctly, it should have been this expression. I should have taken, instead of qx to be this, I should have taken q tilde x to be according to that, whatever.
Therefore, reducing the last term root equal to 0 and reducing the number of variables and having the putative formula point back.
You're just trying to prove divisibility. That is another matter. Yeah, so it's not this. Maybe it's something like this is the expression. There's no point by just trying to figure it out on the board. It doesn't achieve anything. We'll look at the book and find the right thing. But the point is, it's some formula, something like this. This expression is, I believe, correct. The expansion will look like this because it's important that you get these terms. And these two terms are certainly correct. This is Riemann-Roch curve, this is Riemann-Roch surface, and so on. So those things are correct. Whatever Q we have to put, we'll see. It will be the thing which will come out in this calculation, basically. That's the way I would do it. So that formula, this is a little suspicious, that this is the correct Q. Okay, let's carry on. Now I don't need to use this right away. This will come much later in the proof in any case. But I just wanted to write it down immediately, just to say that this expression, whatever it is which is taught, is not something pulled out of the hat just like that. It's something which came from a construction involving exterior powers of some bundle and the top churn class. And the reason those things might be related is because of this sort of thing. At least in some circumstances, they would be related. So that's some kind of motivation for why that class can have some role in the story. Okay, next thing I should do is talk about the Grothendieck construction. Has any of this been done at all? Nothing. Okay. So, if X is a scheme, it makes sense to introduce the following object, K0x, the Grothendieck group of vector bundles or locally free sheaves. On X. And this I define in the following fashion. It's a quotient. It's the free abelian group on isomorphism classes of locally free sheaves modulo, sorry, modulo a certain subgroup. I'll give you generator of the subgroup, and then the quotient, the construction is take the group generated by those things. So for that, I'll write this angular bracket. So if you have vector bundles E, E prime, and E double prime, I'll look at the difference between E and E prime plus E double prime such that 0 to E prime to E double prime to 0 is an exact sequence. Of vector bundles. So take all possible exact sequences of vector bundles. For each such sequence, write down an expression. Middle one minus the sum of the other two. Each of these elements live in the free abelian group. So I can take the group generated by it inside the free abelian group, and I can form the quotient group. That is called the grothendieck group of vector bundles. Now, why have we introduced this? We've seen already all sorts of invariants where they take values in something. They're defined invariants of vector bundles, but they have the property that if you have a short exact sequence, then the invariants of the middle one are related to the invariants of the two extreme ones. So any such invariant is defined on this group in some natural way with values in a suitable place. So what are such invariants which we know? For example, I can talk about the total churn class. This is now a map from K0x to you take the chow groups of X. Sorry. I should assume, let me see. Yeah. I could take the chow ring of X. I'm just thinking, do I want to take anything else? Well, for that, I have to assume X is non-singular. Otherwise, chow ring in the sense of operator. Yeah, that's what I'm trying to see. Instead of that, think of end of chow star X power series T. And then take the invertible elements. So I have the graded chow ring of X. I have its group of endomorphisms, its ring of endomorphisms. I have formal power series in that, which means the coefficient of T raised to n is some endomorphism. Well, each churn class of a vector bundle is such an operator which goes from direct sum of chow groups to direct sum of chow group. So it's an element of that ring. So the total churn class can be viewed as an element in that power series thing. But it's inside the power series of the following special type. C0 is always 1, remember? So it's 1 plus C1 times T plus C2 times T square plus and so on. And that's how it will look. And what is the group operation on this side? So Ct of E, remember, was Ct of E prime multiplied by Ct of E double prime. So the group operation here for which it's compatible with exact sequences is multiplication. So the total churn class of a vector bundle is in fact a unit, an invertible element in this power series ring of the form 1 plus higher degree terms. Right? Huh? Problem? And these I can talk with the invertible elements, two-sided invertible elements. So I can talk. In any case, yeah.
Because the coefficient of T and the coefficient of T square
may not, but these do commute.
Yeah.
Because, yes, that's correct. So what Kapil is pointing out that the different elements which I get inside the endomorphisms associated to the churn classes of vector bundles form a commutative subring. And all the power series actually take values in, so if A is that commutative subring, they really live in A power series T invertible. The group structure exists. No? Okay. If they're nil.
associativity of
There's no, associativity must be okay. Endomorphisms are associative. Anyway, it doesn't matter. Let's not worry about pedantic things. We know what is meant here. I'm just trying to find a place in which it lives to talk about some group. So, of course, if X is non-singular, I have the Chow ring of X. So, the Chow ring of X is certainly a commutative ring. That's one of the theorems. And I can take the power series ring over the Chow ring of X. So, if X was non-singular, I was allowed to write this. But if X is possibly singular, I'm supposed to look at this and maybe look at some subgroup of this. Okay. So, this is CT. That's fine. But churn works better. That goes from K naught X to end of Chow star X. Let me put a Q there. Do I even want to put any power series? There's no power series anymore, right? I guess that is. If I want to think of churn as involving a bunch of, I guess how to say, churn is just an expression, so there's no power series. I just noticed some sort of nilpotence property is valid automatically, so though I a priori wrote some infinite expression, there are only finitely many terms. And now the point is, this is a ring homomorphism. And again, instead of this, if X was non-singular, I'm allowed to instead just put the Chow ring of X itself with the rational coefficients. Alright, so when X is non-singular, I was able to think of this smaller thing and everything lands there. Okay, so this is one of the good thing of the churn characters, it takes values in the Chow. From now on, let me not bother to, it's true, one can do the Grothendieck group construction without assuming non-singular. From now on, let me assume X is non-singular, not get into this headache every time. Okay? So I'll freely use the Chow ring instead of end of Chow lower star as far as possible. Okay. Maybe in the middle for calculations, I'm forced to introduce the other thing here and there, but we'll avoid it as much as possible. So the point is, we have any kind of invariance of vector bundles taking values in some group, and we have the property that whenever you have a short exact sequence of vector bundles, the invariant of the middle one is the combination of the invariants of the two extreme terms in that group structure. Then there would be an induced group homomorphism from the Grothendieck group to that group. That's the general Grothendieck construction. Okay? So we've got that Grothendieck group of vector bundles. So what are some of its properties? For example, suppose, like I said, so suppose f x to y or y to x, the morphism between non-singular varieties. Then I can write a diagram like this. This is just induced by pullback of vector bundles. So that's what it does on the generators. And the relations are clearly satisfied. In other words, I have a short exact sequence of vector bundles on X. I pull each of those vector bundles back to Y. I can pull the whole short exact sequence back to Y also. So a relation here gives me a relation there. Therefore, there's an induced map on quotients. So there's such a commutative diagram is just saying that the Chern classes are functorial, which I asserted. I asserted for non-singular X. For non-singular varieties, any map fx to y, f upper star of ci equals ci of f upper star. I asserted that this is true. I didn't justify very carefully the proof, but I said, once I know things in terms of the splitting principle, I know that this compatibility holds for line bundles, it's okay. And it does hold for line bundles because that's how the multiplication for the Chow ring works. The functoriality map on the Chow ring, in the case of the Chow group of divisors, is just the pullback map for line bundle. In other words, the map, I'm saying that if I take Chow upper 1 x, which is just pick x, remember. It's isomorphic to pick x by using C1. Pulling back line bundles is the same as pulling back the class in chow upper 1. We know that that's part of the functoriality. And because we know everything works, pullbacks work well with line bundles, they work well with the churn class of vector bundles thanks to the splitting principle. I had written down these properties yesterday and I was told they've all been covered, you can skip it. So I'm skipping it. Okay. So functoriality of the churn class for arbitrary maps follows from the fact functoriality holds for line bundles and first churn class and the splitting principle. It's not an obvious statement in some sense. In any case, I can certainly construct this diagram thanks to all those remarks. Yes? I wasn't there. I know what he managed to do. Yes, exactly. That is the method. Yeah. That is the method. Not as such directly. Yeah. Right. No, that constructs a map F upper star on the chow rings. And I'm saying that map which he constructed will have the properties that this diagram commutes. And because this diagram commutes and the splitting principle, churn classes are functorial. Okay, that's the background there. Now suppose f x to y is a proper map of non-singular varieties. Then I can ask, what about is there a proper push-forward diagram analogous to this? It's natural to ask. So at the chow level, we do have f lower star. Well, let's write it like this: chow lower star y with or without q coefficients to chow lower star x. Proper push forward. Right, this was a fairly straightforward thing. I didn't need non-singularity. I think properness is enough for this. But then what about a possible f lower Shri k naught x k naught y to k naught x? That's something we have to think about. So that, let me discuss a little bit and then maybe we stop for today. So I'll try to say what we might do here, which ought to be related in some fashion to proper push forward of cycles. The point is, I can similarly write something else called G0x. This is Grothendieck group of coherent sheaves, coherent OX module, which I define in the following fashion. It's the free abelian group on coherent sheaves modulo a very similar looking definition. Again, coherent sheaves have a notion of exact sequences. In fact, the notion of exact sequence of vector bundle is just a particular case. And exactly like I did earlier, for vector bundle, I can form a quotient. And I can ask myself, for example, are there invariants of coherent sheaves which have the property that if I have a short exact sequence of coherent sheaves, then the invariant of the middle one is the sum of the two invariants. This would be the universal such thing. But the question is, why? The reason to introduce it might be if you can think of such invariants directly, which are interesting. So I claim we do already know some such invariants in the following fashion. Suppose x is, example, x over k is proper. Then I can associate to f chi xf, which is sum minus 1 raised to I, dimension of hi xf, the Euler characteristic of f as a sheaf. Right? This is a number. And it does have the property that if I have a short exact sequence of sheaves, then there exists long exact cohomology sequence. In cohomology, but an important part is with only finitely many terms which are non-zero. But that implies chi of f is equal to, one way of saying it is chi of f prime minus chi f plus chi f double prime is equal to 0. Sorry? Yes, to define chi, but I'm saying that there is a long exact sequence, and the existence of a long exact sequence gives me additivity of something. The sequence better be a bounded sequence, right? That's the point I was just trying to make. Which is of course true. The reason it's bounded is because individually the cohomologies vanish beyond some stage. So I'm saying a very natural invariant which we wanted to study, the Riemann-Roch theorem, is about studying chi of sheaves. So that's such an invariant. So it naturally lives, in fact, on the Grothendieck group of coherent sheaves. So the Grothendieck construction is relevant to the Riemann-Roch theory in some fashion. Okay. There is a natural map K0x to G0x. And this makes G0x K0x module. The map is just take a vector bundle, think of it as a coherent sheaf, and it has a class in both places. So that's the map. And when I say it makes it a K0x module, K0x, I should have said K0x is a ring. Only with the ring I can make sense of something being a module. With E, class of E multiplied by class of E prime is equal to class of E tensor E prime. I did that? I know. Somebody should have objected there. What's the multiplication? No? Nobody objected, but maybe. I said ring homomorphism. I wrote it explicitly. Yeah. Yeah. Of course, I'm just being pedantic here and saying the ring structure is this, but this also tells me what the module structure is. The module structure is class of E times class of F is class of E tensor F. Looks the same, but now the difference is this is vector bundle and this is a coherent sheaf. Okay, so this is an operation of this on that, of K0x on that, compatible with the multiplication on itself. So that's the same as saying this is a module one. Okay, you have these things. So of course, because of generalizing that example which I did here, one does have a map like this, F lower Shri, F y to x proper implies there exists a map which I'll call F lower Shri, which goes from G0 of y to G0 x, which sends the class of sheaf F to some minus 1 raised to I class of Ri F lower star F. This is the ith higher direct image sheaf. So let me just remind you, Ri F lower star F is the sheaf associated to the pre-sheaf which sends an open set U to Hi on F inverse U, F restricted F inverse. This is one of the definitions. The other definition is little f lower star on sheaves, the direct image sends coherent sheaves to coherent sheaves, is left exact. The category of sheaves has enough injectors, right? Injective resolutions, derived functors, etc. Okay, either thing, and they're equal. And it is the case that for such a map Fy to x, Ri F low star of F is equal to 0 if I is bigger than max of any fiber dimension. So in particular, it's certainly true if I is bigger than the dimension of the domain X. The Ri is vanished. Domain Y, sorry. So therefore, there are only finitely many of these, so the alternating sum makes sense. Each Ri is coherent. So this is a formal, is a virtual coherent sheaf, and so therefore it's an element of G0. And it does have the property that if you have a short exact sequence of Fs, you have a long exact sequence of Ris. Again, it has the property that only finitely many Ris are non-zero. So it's a long exact but bounded. And so this kind of generalized Euler characteristic adds up properly. So F lower streak makes sense. Okay? No, I don't ask that yet. I want to construct a map on the K0 level is what I want to do. So let me just state something then, and then maybe stop. This is a key proposition. It's called the resolution property. If X is non-singular, then K0x to G0x is an isomorphism. So next time I'll discuss the proof of this, I'll sketch the proof of this. But granting this, I can now define, I can look at the following thing. I can look at F y to x proper morphism of non-singular varieties. And I can look at the following sequence of steps. Sorry, K0y goes to G0y, goes by that F lower streak which I discussed there to G0x, and then this is isomorphic to K0x by the inverse of that isomorphism. I can consider this sequence of steps. Okay. And then therefore I can look at this composition and I can call this F lower streak. And now it makes sense to ask the question, as Nitin suggested one does, natural question. What about the commutativity? Okay, and the Grothendieck-Riemann-Roch theorem says that it's not commutative, but I can do an isomorphism here by something like multiplying by the Todd class of the map F, whatever that means. This is an isomorphism, and then afterwards it does commute. So this doesn't commute, but this commutes. That's the Grothendieck-Riemann-Roch theorem. Grothendieck-Riemann-Roch theorem is going to say the original diagram doesn't commute, but after changing, composing the Chern character on Y with something which involves a Todd class, I call it the Todd class on a map F. I'll explain everything later on. But it's an isomorphism, whatever it is. Todd class, remember, looks like 1 plus higher degree terms. So multiplying by that is an isomorphism, right? So in the graded context, and then after that it will commute. Okay, so we'll stop. Of course, this is important, we have to prove it. It's not an obvious fact.